speaker, okay, our last speaker for today is Rufin Van Rullen from Cerco, and he will be talking about ongoing projects.
So I'm going to describe to you how neuroscience has been an inspiration for AI in the past and how we can hope that it continues to be an inspiration for future developments in AI. So AI has gone through many different phases, and it's always tried to copy the brain in some way, but maybe in initial stages of AI, like back when it was mostly symbolic AI, then really it was about psychology, trying to copy the behavior of the brain, but it didn't care so much about internal mechanisms. But that's not so true now that we're in the deep learning era, so basically based on neural networks. So there's clear neuroscience inspiration here. So you all know that in the brain, information is processed by biological cells called neurons. These neurons integrate electrical signals that come from other neurons on synapses. Synapses are the names of the interneuron connections. So the neuron integrates this information, it generates its output signal that will be conveyed along the axon to other neurons connected to this one, and so on and so forth. And so we've known this for more than 100 years, and back in the 40s, two American scientists called McCulloch and Pitts had the idea of creating a formal mathematical model of this biological neuron. And so the model is illustrated here at the bottom. You see that the electrical input signals are captured by the variables, going the wrong way, captured by the variables x, x1, x2, and so on. They will be conveyed to the neuron through synapses, and the synapses are represented by parameters that can be tuned through learning. These are represented by these synaptic weights W. Then the neuron is going to integrate, sum these signals, go through an activation function to generate an output, and this output will become the input of other neurons, and so on and so forth. So it's important to keep in mind that this model neuron is, it's 80 years old, but it's actually still used today. When you talk to ChatGPT, it's a neural network, and inside this transformer network, there is exactly the same types of neurons. So to be a bit provocative, I could say that nothing new or revolutionary has been invented in the last 80 years. Or I could actually argue that this is mainly the main and maybe the sole contribution of neuroscience to today's AI. Okay, so you can train these systems to do specific functions by tuning these synaptic weights. Of course, a single neuron is not going to do a lot, but what you can do is take this neuron and embed it into a very large network with many layers. That's why we talk about deep learning, when it has many layers. And each of these layers will have thousands, maybe millions of neurons. And when you have an architecture like this, you can train it to perform quite complex tasks. For example, you could present to it an image. At the input layer, the information would go through the different layers, and at the output, you could ask the system to classify. Maybe at the beginning of training, it will make a mistake. It will say it's a dog, but it doesn't matter. You know the right answer. You know it's a cat. That's called supervised learning. And so you can compute an error signal, and then you can send this error signal back inside the network, and you can use this signal to tune the weight of these synaptic connections here, all the connections between neurons, so that the next time you present an image like this one, the network will be more likely to say cat and less likely to say dog. So this is called backpropagation. And again, that's really what's driving modern neural networks and modern AI in general. So this is a type of network called convolutional network. It's typically used for image classification or sound classification. There's many other neural networks. For example, transformers are used in language processing, in LLMs. We have recurrent networks used to process sequential data. Diffusion models are used to generate, for example, images. And we could argue whether some of them are more biologically plausible than others. Probably convolutional networks and recurrent networks are more biologically plausible than transformers or diffusion models. But actually, that's not what I want to do today. I would rather focus on the large-scale organization of the AI systems. We're now in an era where we have the tools and we have the computational resources to create much larger scale systems with a subset of these models that can jointly solve much bigger problems than each of these networks could solve individually. But how are we going to go and design these large-scale systems? You could go at it totally blindly based on a gut feeling, on intuition, and I'll show an example in the next slide. Or you could turn to neuroscience and ask, does knowledge of the brain get you something, get you some inspiration about how to design these systems? And that's what I want to describe, some existing neurocognitive architectures that we could use as blueprints for these large-scale systems. So the first system I want to talk about is called JEPA, the Joint Embedding Predictive Architecture, that was proposed a few years ago by Yann Lequin. It's been all over the news lately for various reasons. But here, so you have an example of Lequin's vision about how we could move beyond existing LLMs and transformers and create the next generation AI system that could solve problems that LLMs cannot solve. So in his vision, he's got perception modules. Oops, always going in the wrong direction. He's got perception modules, action modules, maybe a world model interacting with short-term memory system for computing a reward. They're all connected in different ways. They interact in different ways. But what's important to keep in mind is that Yann Lequin is not a neuroscientist, and he's basically pulling this architecture out of his hat. But he's putting a brain picture in the background just to justify that this is probably what the brain would look like. But it's all based on intuition or maybe introspection, what he thinks a brain should be like. Now, I don't want to complain about this model. There's probably a lot of very good aspects to this model. Some of these components are probably very useful if you want to design a brain. But what's sure is that it's not inspired by neuroscience, or it doesn't take into account neuroscience. So does neuroscience have anything to say about this? Well, actually, yes. So I want to describe a couple of models that have been proposed by neuroscience to account for large-scale cognition, and that maybe we could use as a blueprint for these large-scale AI systems. So the first one I want to talk about, so to be clear, I'm not going to compare these models. I'm not going to argue that one is better than the other. I just want to show you that it exists. So the first model is called the Common Model of Cognition. It was created as basically a consolidation of two prior architectures that were developed at Carnegie Mellon by very famous computer scientists like Alan Newell, Paul Rosenblum. So the first one was called the SOAR model. The second one was called ACTR by Anderson and LeBeer. And so they joined forces to create this common model of cognition. And it looks a bit like this. So it's all centered around working memory system at the center, which is bidirectionally interacting with a perception module and an action module, and also with other memory systems like a procedural memory, a long-term memory system. All of these components map onto particular regions of the brain, and there's been proposals about how you could implement a system like this in AI. Now, importantly, when you look at this, you might think, well, this is actually not very different from the JEPA architecture, right? I mean, you can find a lot of similarities between the components. And I agree with you. I think the main difference, if you think about it, is that this system predates JEPA by about 30 years or so. But aside from this, there's lots of similarities. And this one is backed up by a lot of neuroscience data. And it's confirmed also by a lot of neuroscience experiments. Another architecture that's been proposed is the so-called hub-and-spoke architecture by Patterson and Lambert-Ralph. They proposed it as a model of semantic cognition. And again, you find a lot of similarities with the other systems. At its heart, it has a hub for semantic memory, which is connected in a bidirectional way to different systems for perception or action, like vision, sound, speech, praxis, and so on. And it maps onto particular regions in the brain. And the final model I wanted to mention, that's my personal favorite, but I said I wouldn't compare them. So it's called the global space theory. It was proposed by Bernard Bars in the 80s and the 90s. And so what it says in a nutshell is that the brain would be composed of many different, so this is an illustration of the brain in this theory, these circles. The brain would be made up of many different regions that specialize for different functions. So these are represented here by the gray and white branches in the periphery. You might have regions specialized in vision, in language, in action, and so on. And these regions can function entirely independently from each other. They don't need each other to function. But under some conditions, a subset of these regions might be selected by an attention process. And then these selected regions would be granted access to the central workspace. And that means that the information in the workspace is now going to be broadcast, distributed to all of the other regions in the brain. And this broadcast is important because it accounts for our unified conscious experience. It basically explains why every part of the brain knows what's happening here at the center. So when you think about this theory from the point of view of AI, you realize that definitely in AI today we have something like the branches of the graph. We have very good expert systems for, for vision, for language processing, for action, and so on. And so if we want to implement this, we don't have much to do. Maybe all we have to do is create the workspace at the center that allows these different systems to communicate. And so that's actually what we've been trying to do in the ANITI chair that I'm part of, with our model that we call the global latent workspace model. So basically what we're trying to do is to connect many different pre-trained modules for different functions, and we might even keep these modules frozen, and we just try to learn a central representation that allows these systems to communicate and exchange information. So it's really a question of representation learning, and our main training objective is a representation learning objective, but we also focus on the idea of broadcast from global workspace theory. We try to make sure that in the system, the central representation can be redistributed to each of the modules in a format that they can understand. And so this gives us nice properties about semantic grounding or affordance that I don't have to describe here. And it also means that the final representation, the central multimodal representation, has very useful capabilities that we can use for downstream tasks. And I'm going to show an example in the context of reinforcement learning. So here you're going to see a simulated robotic environment with a robot in a factory. And what we did is we trained a global workspace system to learn a sort of mapping, a sort of shared representation between two modalities, two modules, one for vision from the point of view of a camera, from the robot's point of view, and one here on the right for what we call proprioception, which is just a set of numbers representing the robot in its environment. And so we can learn a global workspace representation, and we can compare it with a baseline system. And so we're comparing it with CLIP. CLIP is a system that was proposed by OpenAI. The only thing it does, using contrastive learning, is to align the two domains in a shared representation. But it doesn't have the ability to go back from this central representation to the initial modules. It doesn't have the ability to broadcast information. So now we have these two multimodal representations. We can train a reinforcement learning agent on top of them to perform a very simple task in this environment where the robot will have to go and find a table. And when it reaches the table, it gets a reward. And so in the movies on the top, you're going to see the situation in which the system was trained. Initially, it was trained to perform the task based on the numbers in the black box. That's all the information it had. And so we can run through some episodes. You see each time the table is at a different location, the robot gets to the table, and then it gets a reward. The screen is going to turn green. And you see that both our system and the CLIP system can solve the task fairly well, no problem here. But now what we're going to do in the movies at the bottom, we're going to take these agents out of their comfort zone, and we're going to ask them to do a new task, but without any retraining. So it's called zero-shot cross-modal transfer. We ask them to apply the same strategy as before, but now we're replacing the numbers by a camera image. So we're using a different input modality. And you see that the global workspace agent has no problem solving the task, applying the same strategy, generalizing to the new situation, but the CLIP agent is really struggling. It just can't do the task anymore. So there's really something special about the global workspace with the broadcast property, because that's the only difference between the two systems. Okay, we have another demo that I'll just go over very quickly for the sake of time, but just to show that this system also works in what we call model-free reinforcement learning. So in this case, we couple our global workspace with a world model, and so that allows the system basically to train with fewer environment steps because it's training in its internal world model, like a simulation environment. So this is similar to the Dreamer idea that was published by Google DeepMind in 2025. And just to make a long story short, what we find is that when the world model is connected to the global workspace, it can learn the task much more efficiently here with about 5 to 7 times fewer environment steps than the standard Dreamer system. Okay, so this is one aspect of the global space. We can use this central representation for downstream tasks like reinforcement learning. There's still something missing to our global architecture. You remember that we want to be able to select some modules dynamically for inclusion in the global workspace. And so that's something that we worked on recently. We just added to our system an attention controller that dynamically decides, by looking at the state inside the global workspace, dynamically decides which modules should be connected to the workspace, and it can change its mind at different time steps and so on. And just to show you how it works, we performed a study on 2 separate multimodal benchmarks. One was called Simple Shapes. It's on the figure on the top. The other one is called IMDb. It's based on the movie database at the bottom. And so what we're doing here is we're going to voluntarily corrupt some of the modalities in this benchmark, but we randomly draw on each trial which is the corrupted or which is the clean modality, and we just would like our attention system to dynamically detect which is the good modality and focus its attention on this modality. And that's exactly what happens, so we can train our system on one of the classification tasks, and then we can either test it on the same classification task, that's called in distribution in the plots on the right, or we can test the same system, but on another classification task that it hasn't seen before. That's the out of distribution setting. And so when we compare our model to existing baselines, other attention models from the literature, you can see that they can all learn to do the task, to focus attention on the right module fairly well in distribution, but as soon as they have to generalize to another classification task, the other models tend to collapse. They need to be retrained, whereas the global workspace doesn't have this problem. And so to conclude, the take-home message is that there are neurocognitive architectures out there that you can use to guide the development of new AI systems. You don't have to go at it blindly. In the C3PO Synergy Chair, we focused on one of these systems, the global workspace, but it's not the only one. We've already demonstrated promising abilities for these systems, and I want to point out that this is not work that I do alone. It's a synergy chair, and so we have combined expertise with people working on language, Nicholas Asher, working on perception, Thomas Serre at Brown University, or people working on robotics at the LAS. And jointly, we hope to be able to join forces and use this global workspace architecture to create something like the next generation AI. Thanks, and yeah.
Thank you, Rufin. So we have time for one quick question. Is there any question for Rufin? Yes.
Thank you for this good presentation. The question is, today, what are the size of the models you are using? And the question behind the question is, do you plan to embed this architecture into a small robot? I mean, so that, and the question is, how much of resources you will need to do that?
Yeah, so the models right now are fairly small, but they're sufficient to do exactly what you suggested. So we're working on this. So I showed some simulations, but some of these simulations, we can actually port them onto an actual robot. So we're working with Olivier Stas to actually move this onto quadruped robots in the LAS and help them perform simple tasks. That's doable. If the question behind this is it competitive with LLMs or reasoning models or something like this, at this stage, we're not talking about the same parameter size for sure. But I think it could be competitive if we just had the training budget, which we don't have. So.
Thank you. Thank you, Rufin. I think we'll close the session here. So please thank all the speakers again.